Hello everyone and welcome back to another video. Today I really just want to play around and kind of answer some basic questions and derive some nice equations relating to this here lemniscate. And yes, that is how it's pronounced. So I'm like 90% sure. There's a reason as to why I started a math channel and not an English one. But yes, I'm pretty sure it's called lemniscate. So basically what it is right here is this right here is generally what's referred to as lemniscate. So it's this infinity sign sort of shape. But if you just kind of change the formula slightly, replacing this, so this A here is normally a 2. If you replace that with an A, you get kind of an abundance of shapes. So I put the link down in the description if you'd like to check it out. But if you just kind of move this A, you'll see that we get something resembling like the normal rows pattern you normally see in polar graphs. So say we had like r equals sine of a theta. What you'd see is every time we change a, we get like a different number of little petals, right? For even numbers, we get like 2n petals. For odd numbers, we get n or a, pardon me, petals. Anyways, but that's not what we're looking at today. Today we're looking at something slightly more interesting, in my opinion, and that's this right here, the lemniscate. So we're just going to be finding area and perimeter, or arc length if you want, of the lemniscate. So yeah, just a couple of things to note. Whenever you set a equal to 0, you get a normal circle. But for our formula, that's not really, we're not going to worry about this, because in the what you end up getting is a limiting example of like a going to 0, and the formula is not nice, and etc, etc. So we're going to kind of exclude a equals 0 from this, because we know clearly that the perimeter here is 2 pi, and that the area is just pi. Anyways, but yeah, so our main focus is actually going to be a equals 2, but we'll get to that in a second. So, on to the OneNote, enough of me rambling. Alright, now that we're on the OneNote, we can calculate the area of a general lemniscate. So we know that in polar coordinates, our area, just in general, is going to be equal to 1/2 times the integral, I'll plug in the bounds in a second, of just r squared times d theta. And this just comes from the like integrating in general in polar coordinates, but that's for a later video. So yeah, what we have here then is just equal to, this to be bigger, this is going to be equal to right here, is going to be 1/2 times the integral from 0 to, I'll deal with this upper bound in a second, of cosine, actually the absolute value of cosine of a theta d theta. Oh, that should be a normal, should be a bar, not just a parenthesis. Okay, and you might be asking, well, what's the upper bound here? And we can do this multiple ways. So the way I like to think about it is, say we have our lemniscate here, right? I'll just draw the infinity sign for, yeah. If we say a is like 2 pi, we're going to be integrating around the entire thing. But then that means we kind of have to deal with this not so nice looking cosine of a theta. And quite frankly, I don't really want to do that. So instead, what I'm going to do is just say the area of one quote-unquote like leaf, or petal, I guess, of this lemniscate. So there's like that little bit right there. We're going to calculate that, which is just going to be, well, there's 2a of these little petals in the entire thing. So this right here, for example, this is a equals 2, meaning that for this right here, there's what, 4 petals inside the entire lemniscate. So for our formula right here, what we're going to have is just 2 pi, and then divided by, or sorry, pi, just over 2a, and this will give us basically the formula for one petal, so to speak, of the lemniscate. And then to find the total area, we're just going to have to multiply this by 2a. And again, the reason for this is really just to avoid having to like do stuff with this absolute value right here, because on the interval 0 to pi over 2a, cosine of a theta will always just be positive, I believe. So, with that having been said, let's get calculating this area. So, it's really not that bad, it's really not that bad of an integral. So we're just integrating now from 0 to pi over a, or 2a. 0 to pi over 2a, pardon me, of cosine of a theta, d theta, and I'll just put this 2a here, and these are going to cancel. And what we're left with, I mean, this really isn't that bad of an integral. This might be the easiest integral on the channel so far, actually. This right here is just going to be sine of a theta, evaluated from 0 to pi over 2a. And again, this a just goes away because the integration, reverse chain rule, use sub if you like. But yeah. So then plugging everything in here, we just end up getting the sine of, well, sine 0 is 0, so we don't have to worry about this bit right here. But then sine of pi over 2a times a is just sine of pi over 2. And that's just 1. So the area of any, I say any with an asterisk because we are ignoring a equals 0. This area of really any lemniscate of any a is always just going to be 1, which is kind of neat. So no matter how much you increase a, or what I should say technically is for any natural number, the area of the lemniscate is just 1. So yeah, now that we've calculated the area, let's move on to the perimeter, or if you like, arc length. So yes, arc length. This right here is going to be slightly more tricky, and what we're going to do is derive it in general for any a, and then kind of plug in our specific example to kind of, do some fun integration. So, in general, in polar coordinates, arc length is just the integral from, well, we're going to be using our same bound. So for this specific example, it's just going to be 0 to pi over 2a, but in general, it's obviously not going to be that. We're going to have the square root of r squared plus dr d theta squared. And it's just basically straight out of, BC or Calc 2 class, I believe. That's the equivalent. I don't know anymore. Okay, so, and we know that r is just equal to the square root of cosine of a theta. So this integral just becomes the integral from 0, that's a big integral sign, Jesus. 0 to pi over 2a of the square root of cosine of a theta plus, well, dr over d theta. That's just, I'll just write this to the side actually. It's just going to be minus a, changeable, minus a sine of a theta over the square root of 2, or over 2 times the square root of cosine of a theta, which is a mouthful, but whenever we square it, the negative goes away. So we're just going to get a squared over 4 times sine squared a theta divided by cosine of a theta, d theta. And now what we're going to do is just simplify things a tiny bit before we go on. So we're just going to say this right here is equal to the integral from 0 to pi over 2a, same bounds of course. I'm going to zoom in a little bit here. And we're going to have is just the square root of cosine of, I'll just multiply the top and bottom by the square root of cosine of a theta, you'll see why in a second. A theta plus a squared over 4 sine squared a theta over the square root of cosine of a theta d theta. And this looks incredibly messy, but if we kind of look at this a tiny bit closer, we realize that for a equals 2, I should probably write this down here. For a equals 2, the entire numerator right here, so this entire bit, that's just going to equal 1, because what we get is, a squared is just 4, 4 over 4 is 1, and then just by the Pythagorean identity, what we're left with is just, just 1. Square root of 1 is 1. So that's really the main reason. And whenever I tried evaluating this integral with the beta function, it really wasn't that nice with any of the identities that I had on hand. So I'll play around with it more. Maybe I'll make it into like, I don't know, short or something or another video if I evaluate this. But for the time being, we're just going to assume that a equals 2, so we get this slightly nicer integral, the integral from 0 to pi over 2a of 1 over the square root of cosine of a theta d theta. And I'm just going to say, or just do a quick substitution, x equals a theta, so we can get some of this stuff out of here. So for this right here, we're just going to have the integral from 0 to pi over 2, much nicer, of 1 over the square root of cosine of x dx. And yes, there should be an extra a here, I believe. Or no, sorry, 1 over a. Helps to be able to do math. Okay, so yeah, so now all we have to do is evaluate this integral right here, which really is actually kind of fun. So let's get to it, shall we? The first thing I'm going to do is really just kind of invoke this identity over here. So let me try it to the side. We know that beta of some, say, x comma y. I hesitate to use x, I'll be using it a lot, but just humor me. We know that beta of x and y, well, we know we can express that the gamma function, but we can also express it with this nice little integral right here. Sine to the 2x minus 1, I don't know, say t, times the cosine of 2y minus 1, oh, let me scoot it over, t dt. And if we kind of just compare these two integrals right here, we realize that it really is the same. And I am realizing now that we are assuming that a equals 2, so I can just make this a half. Boop, okay. Sorry. Okay, so if we just kind of compare the structure of these two things, we kind of realize that we can just set x equal to 1/2 and y equal to, what is it, 1/4? And what we end up getting is just a multiple of the integral on the left, just meaning that if we take 1/4 of this integral on the right, we'll end up with the integral on the left. So let's do that, shall we? Well, actually, I'll leave this in the frame. That might be helpful. So what we end up getting is just, I'm just going to multiply multiply top and bottom by 2. So we're going to end up getting 1/4 times 2 times the integral from 0 to pi over 2 of, well, this right here. So just cosine to the negative 1/2 of x dx. Meaning that this is just equal to 1/4 times the beta function of 1/2 comma 1/2 comma 1/4. And we know just from the beta function that we can express this in terms of factorials. So we know that this is just 1/4 times gamma of 1/2 times gamma of 1/4 over gamma of 3/4. I can add fractions. And we could just kind of leave it like this. But, I mean, that's kind of ugly, isn't it? I mean, you could maybe substitute in, square root of pi. But still, it's really not that nice. So one thing to clean this up I do want to invoke is one little gamma function identity over here. And that's really just the fact that the gamma function here of, that gamma of just some x plus 1/2 is equal to 2x, let me move this over, 2x factorial over 4 to the x times x factorial times the square root of pi. And you'll notice here that, well, these right here only differ by 1/2, meaning that we can just kind of invoke that. Basically setting x equal to, setting x equal to 1/4. What we end up getting is going to be gamma. I'll write this. We're just going to focus on this little part right here. So we're just going to have gamma of 1/4, then divided by gamma of 1/2 plus 1/4, which is just equal to gamma of 1/4. And then we're just going to invoke our little formula right here. So we have then, it's just plugging in 1/4 to this equation right here. Oh, and we have to say it's 1 over that. So I'm just gonna do that. We're gonna have 4 to the 1/4 times 1/4 factorial divided by 2x factorial, but that's just going to be 1/2 factorial times the square root of pi. And cleaning things up a tiny bit, just to start off with, we know that this right here is just the square root of pi over 2. So we can just kind of, did I put the pi in the right place? Yeah, I did. Okay. Just want to make sure. Okay. So yeah, let's clean that up a little bit. We end up getting this is equal to. So we're end up getting 2 over pi times gamma of 1/4. But then let's kind of ask ourselves, well, what's 1/4 factorial? Like, what's that in terms of the gamma function? And we know that just x times gamma of x is equal to x factorial. We then know that just 1/4 times gamma of 1/4 is equal to 1/4 factorial. And, just summing that in right there, we end up getting an extra factor of 1/4 here. This becomes squared. And we have a 4 to the 1/4 here. Meaning, this is kind of long, I know, but trust me, it's nice in the end, okay? Meaning that we just have 4 to the negative 3/4, which is just 2 to the minus 3/2, then times 2, so it's like a 1 minus that, over pi times gamma squared of 1/4. And simplifying this slightly more, and bringing in the stuff from up here. So the little factor I was missing up here is just this right here, the 1/4 times gamma of 1/2. So we have 1/4 times gamma of 1/2, but gamma of 1/2 is just what? The square root of pi. So we have the square root of pi over pi times 2 to the negative 1/2 times gamma of 1/4 squared. I really set in red, but no, that's okay. Changing colors randomly, that's okay. But this right here is just 1 over the square root of pi, and that's just 1 over the square root of 2. So we can actually just write this finally as gamma of 1/4 squared over 4 times the square root of 2 pi. Which is quite nice, I think, in my opinion. But one also interesting thing to note is that, I believe it's almost by definition, is that the thing called the Lemniscate constant, this little symbol right here, this is just equal to gamma squared times 1/4 over 2 square root of 2 pi. So this right here is just equal to our Lemniscate constant divided by 2. So yeah, that's the area of, that's the area of the little infinity sign, or, pardon me, the perimeter of, that's the perimeter of 1/4 of the infinity sign. So you'd have to multiply that by a factor of 2 or 4, I believe, to actually get the final answer, which is about 5, I believe. But yeah, anyways, I hope you all enjoyed this little thing on Lemniscates. Ran longer than I wanted it to, but that's okay. So yeah, hope you all enjoyed, and I'll see you all in the next one. Adios.